Good afternoon, my name's Tim Dwyer and welcome to the webinar today. I'm visiting Professor in Building Service Systems at UCL in London and Technical Editor of the CIBSE Journal, and also past chair of and current Programme Officer for the CIBSE ASHRAE Group. And I'm really pleased to be with you today, together with hundreds of others around the world, to chair this webinar, which is entitled Zone Fire Modelling and CFD Analysis. Throughout the presentation, there's a question panel on your screen, and you can type in questions at any time. And John will respond to those questions at the end of the webinar as time allows. He's been kind enough to say that if we don't get through all the questions online, he will pick up those questions later, and we will post those answers on the CIBSEASHRAE.org website. So let's move forward with today's webinar. And first of all, I'll introduce our speaker. Dr. John Klote is known throughout the world as an expert in smoke control due to his many books, technical papers, articles, presentations. And he had 19 years of fire research that contribute to his knowledge and experience whilst working at the US NIST. For 11 years since leaving NIST, John has operated his own consulting company specialising in smoke control. He's a fellow of the Society of Fire Protection Engineers, a fellow of ASHRAE, and a member of the National Fire Protection Association, as well as being a registered professional engineer in Washington, DC. So without further ado, I pass across to Dr. John Klote, who's speaking live from Washington today. Over to you, John.
Thank you, Tim. Okay, introduction. Zone fire modeling. Just quickly, that's a simple form of modeling that was developed towards the end of the 20th century, and it consists of a smoke zone which is located under the ceiling of the fire room, and a lower zone, and the lower zone would be smoke-free or nearly smoke-free. The focus here is on the model CFAST, and I'll explain why. That'll be obvious later on. Computational fluid dynamics, for people who are not familiar with it, it's a method where we divide the space that we're interested in into a very large number of cells, and we solve the governing, or we have the computer solve the governing equations for those cells. Tenability analysis is used to determine if a space is tenable, and we evaluate toxic gases, heat, thermal radiation, and reduced visibility. Atrium smoke filling will be discussed later on. That's a form of smoke control for atria where we can eliminate the fans. So that's really quite a nice arrangement. As far as CFAST is concerned, you can, when you download CFAST, you get a technical reference guide which has all of the information about the model, the technical information, the equations, and so forth that are used in the model. I have the authors there. You can read them probably faster than I can say them, so I won't get into that. The user's guide, which is much more for design engineers, much more of interest, and the authors are listed for it. Also, I'll be talking about the Handbook of Smoke Control Engineering here, and here I'll just call that the Smoke Control Handbook for short. And the idea of a zone fire model came from people back in the I guess, 70s and early 80s of viewing small room fires. And in the early stage of the fire, we get a plume, and it goes up and hits the ceiling of the room, and the smoke spreads out. And then as time goes on, the smoke layer falls, and it'll fall such that it'll flow out the door of the room. And the idealized model is like this. This little figure represents it. And we have here a smoke layer, which is uniform throughout as far as the concentrations of contaminants. They're the same everywhere, and there's one temperature for this layer, so it's simplified. The interface between the smoke layer and what's below is a perfect plane. If you're just a millimeter below, you get the same gases that you would have for all of this area here. If you're a millimeter above that space, you get the same contaminants that you get everywhere. And so that's a little artificial, but it's useful. The fire is not a fire that's simulated. You input the heat release rate as a function of time, and you can also put in information that can give you the soot particles that are in the smoke, and also chemical constituents. The plume is, again, we're not simulating a plume the way you would in CFD model. We're using a algebraic equation for a plume that's been based on quite a bit of research. And there's a number of these equations around. And the door jet is another empirical equation like the plume equation. To go over this again quickly, the smoke layer is at one temperature, and throughout it, it has uniform contaminants. The interface is a perfect plane. The space below the smoke layer is smoke-free or has just a slight amount of smoke in it, depending on the particular zone model that you would be using. And the plume and door jets are both empirical equations. There were many of these models developed in the 20th century. Today, only 2 of the models are supported by, and I mean by supported, that they're the organizations that you can get the model from still will respond to your questions about the model, and they still keep the model up to date as far as technical changes and also changes in the computer hardware, so that you need to modify the model. CFAST is free from NIST, which is a big plus for CFAST. You download it from this web page. This is very important. I made the mistake, I don't remember, a few months back, of Googling a download page for it and downloading it. And what I got was a version of CFAST that was slightly out of date. I got the documentation that was slightly out of date, and I didn't get any example files. And I went and, because I can drive over to NIST and talk to the people that are in charge of this, Rick Peacock and Paul Renique, and they told me, no, I need to download it from this page in order to get those things that are correct. CFAST is unique. There are very few computer models that have passed the verification and validation program of the U.S. Nuclear Regulatory Commission. And that means that it can be used in the United States for design analysis for nuclear reactors. And that's a big plus for the model, because it means that it has we have a lot of confidence in what's in it. The verification verifies that the model is the way that the mathematics that are published for it say it's supposed to be, and the validation says that there have been experiments to show that what it produces is realistic. And the model incorporates tenability, which makes it very useful. Using CFAST, you want to use the documentation from CFAST, the user guide. Also, Chapter 8 of the Smoke Control Handbook has some additional information relevant to smoke control use. Start with the example runs that within CFAST, and then go ahead and modify them. That is clearly the best way to go. And save often. Now, I don't say save often the way you normally think it's said. Normally you think, oh, I'm saving it because I don't want it to crash. Well, that's true, but it doesn't crash. That's pretty stable. But there's a strange thing about it that I found. Sometimes when you put in data and then you move on and put some more data in and put some more data in, it may forget some of the data you put in. But if you save after every time you put the data in, then it definitely remembers. So save often. CFAST can be used for design analysis of atrium smoke control systems. In the United States, that would be allowed in NFPA 92. I would not recommend doing that, but you can do it. I would go with other methods. The equation method or a CFD. It includes sprinkler and detection activation models. And because of the sprinkler activation, we can use it to develop design fires, and they can be for CFD or CFAST, or in fact for the equation method of analysis. Tenability analysis, this is used a whole lot with CFAST, and we're talking about the threats to life: exposure to toxic gases, exposure to heat, exposure to thermal radiation, and reduced visibility. And it may seem, if you're not familiar with this, that it's almost a non sequitur to have these exposures. And then we talk about reduced visibility, but you become disoriented in a fire, and then that prolongs your exposure to these other threats above. Plus, in a reduced visibility in an atria situation, there's the threat of falls. And so that's very important. There are equations and also graphs for all of these above threats. They're in the handbook of smoke control engineering. And usually, now this is not always, but usually, if visibility is okay, then the toxic gas exposure would also be okay. Now, that doesn't mean that that's all you should look at. You still need to consider the other exposures. The equation for visibility, I have here one of Jin's equations. There is another one that you can also use, but it's completely equivalent to this one. And it's that the visibility equals a constant divided by this constant and the optical density. And The constant K equals 8 for lighted, illuminated signs, ones that are lit up, and 3 for reflecting signs. And the 3 we also will commonly use for things like being able to see walls and doors and railings so you don't fall, that type of thing. There is no consensus for visibility distance and for should we calculate for reflecting signs or illuminated signs. Jin gave criteria on the distance that was 4 to 14 meters. The 4 meters is for locations where the occupants are very familiar with their surroundings, the way they would be inside your home. And so for commercial buildings, the 4 isn't so good. Values I've seen people use a lot are 10 to 14 meters. And I'll mention that later on. The smoke filling works like this. In the early stages, and this is good for really only a very large atria, we have a fire and a plume rising from the fire, and we formed in this picture the sealing jet. Now, if this is where we're in, these arrows are all air that's being entrained in the plume, and if this is tall enough relative to the size, the heat release rate, and the contaminants, and the soot generation in the fire, then we can have tenable conditions up here in this sealing jet, and you could have people looking at the fire while it's burning in the early stages. Not only that, but while a lot of people, they would hear it and leave, a lot of people would be so interested in this, and they would feel safe if they were far away from it, staying there, especially if they weren't far from a exit, so that they could just, you know, walk a few feet and go into a stair door or something. And so even though this is not what we tell people to do, we don't say stop and watch the fire. That's what human nature tells them to do. And so they'll probably be doing that. Now, if the fire, as it progresses, it drops down. And you notice here that we are still in training, but now what we're doing is we're entraining smoke into the plume, and then it's going into here. So that makes things worse than they would have been otherwise. Again, if the fire is such, and what's being generated there is such, this could still be a tenable environment here and in here. It falls further and we're entraining more smoke. Again, if the same thing can be said about tenability, and we drop down even further. Now, almost all the plume is entraining smoke. But again, if the atria is big enough, it can still maintain tenable, it can be tenable for some period of time. And it can also go all the way down. You notice in the little figure here, we have less people, more and more people decided it would be smart to leave. When you're in this smoke, even though it's tenable, it can make you somewhat nauseous. You may feel bad. And so it would be natural for a lot of people to want to leave. Some of the technicians I knew at NIST were really tough guys. And we would have smoke where I would leave and most everybody else would leave. And some of those tough guys would stay there and you know, not be bothered by it. Anyway, on the atrium smoke filling, as I mentioned earlier, it eliminates the equipment. You don't have the exhaust. You don't have to worry about makeup air supply. There's a lot of nice things like that about it. You basically can save money. Clients like that when you save money. Design analysis, I strongly recommend using CFD and tenability analysis when you're designing these things. You want to maintain a tenable environment, and that's the approach that gives you a high level of confidence that you do maintain a tenable environment for the design fire. Evacuation time, in fact, can be more than the filling time because you're maintaining a tenable environment. CFAST can be used to give you a very rough simulation of what's going on, but it can be used to give you an idea of the feasibility of using atrium smoke filling. So that's nice. And with one of these smoke filling systems, you may need to get code approval. I know in the United States you would need to get code approval. From my knowledge, everywhere. I did some simulations to look at smoke filling, and I did a layout like this. This is a cube, and we have the X, Y, and Z dimensions for the cube. And we have a air vent here, which allows for the expansion of the gases from the fire, and also some oxygen's coming in here for the fire. And the fire is located here a little bit above the floor. And actually, in this case, I put the fire at the floor level, now that I think about it. And so we used this design fire. Now with design fires, you could use a whole lot of design fires. This Atria, I looked at it as being what we would call here a sterile Atria, in that it has virtually nothing that burns, or nothing much that burns. You may have a sign-in sheet where there's a little bit of paper there and a clipboard where you would sign in when you come and go at maybe a guard station or a receptionist station, something like that. You may have that kind of a thing, but you wouldn't have objects made out of wood and so forth in one of these things. You may have some plants that have water, you know, in them, the dirt, you know, soil, that type of thing. You may have a little bit of that, but not much. And so your fuel would be transient fuels. And transient fuel is a fuel that's in a space for a short period of time, ideally. Sometimes, of course, people put them in and they wind up in for a lot longer than a short period of time. Like they'll put in an atrium, maybe a automobile that they're showing for you know, sales purposes or some other reason. And I saw one case where the transient fuel was mattresses, and they were in a student dormitory, and they piled them up in the basement right next to the elevators, which is a good smoke shaft. And they were waiting to be delivered in the next term. So that's certainly a long time, but usually they're not that long. Here I'm looking at a sofa as my transient fuel. And the logic behind that would be something like the loading dock is not far from the atria, so you can bring it in and set it there to keep the sofa nice and clean. You don't want it to get dirty on the loading dock. And then in a day or so, that would be taken on up to an executive's office in the building. So that's a logic that could be used for a sofa. And this is a reasonably good fire. We see that it's a little more than 3 megawatts. And it's 90% polyurethane foam. Polyurethane foam has a very high soot yield, and that means that it has a very it's a challenging smoke to deal with from a visibility standpoint, and it needs to be diluted a lot so that you can see well through it. And the little bit of cellulosic material would be the wood frame. Now, if you have 10% cellulosic material, you don't take the sofa and say, oh, 10% of the weight is wood, and so we'll say 10% of our fire will be cellulosic material. If you've ever witnessed one of these burns, you see when the burn is over, there's a good portion of the frame of a sofa or a love seat or a upholstered chair. There's a good portion of the frame left behind. It doesn't burn that all away. And so if you were like 15 or 20% cellulosic material, then considering 10% as being what's burning makes sense. So here's what we get from looking at these. And remember that we said that for commercial buildings, our range of visibility is very often 10 to 14 meters. It might be less than that for in some cases. So now we look at the first one. Now I would have thought, before I ran this, that the 30 by 30 by 30 would have done better with the sofa fire. But the sofa fire is pretty nasty because of all of that polyurethane foam. And it turns out that it doesn't do well at all. If you had a different design fire, it might do much better. It would do much better, most likely, or, you know, likely. Now we look at the 50 meter cube, and we see this, the reflecting sign doesn't do that well. But it's good enough, it's over 4 meters. It's good enough for you to see a hand railing before you get to it and fall off. It's good enough to see a nearby door and like an exit door and that type of thing. So it's not bad from that standpoint. Now, the 11 meters is that you're at the bottom threshold of this range here, near that bottom threshold. So you can see them. So you could possibly decide that that would be appropriate for your smoke filling system, your performance. Now, I looked at a 70 meter cube one, and we see that we're 8.6 meters of visibility for a reflecting sign. That's not quite what we normally use. Some people have used values lower than the 10, and so that's sort of up in the air whether that's good enough. As far as the illuminated sign, there's no problem there. That's really very good. With this one here, you probably, if you were going to go that route in a big atria, you'd probably have to add extra exit signs that are illuminated so that people could see to them and then go to the next one beyond. Then we get to a summary. Tenability analysis can evaluate these threats, and you can read them again faster than I can say them. CFAST can be used to develop fires for CFD simulations, CFAST can be used to help determine if atrium smoke filling may be feasible. You don't really know for sure if it's feasible from what it says. It can tell you that if that was your design fire on that earlier table, and you had the 30 meter cubic 1. That tells you that it's definitely not worth wasting your time on doing a CFD analysis to design the thing. But CFD simulations along with tenability analysis are recommended for atrium smoke filling systems. Okay, do we have questions now?
Thank you, John. That was excellent. And yes, we do have some questions. So I'll run down the questions. They may not be in strictly the order that it seems logical, but we'll run through these, and hopefully you'll be able to respond to just about all of these. Please carry on typing in your questions. There's a question box on your screen, so just type in questions. I'll read them out to John so we can all hear them, and John will attempt to answer them. So let's go for our first one, and our first question is from Gary, and Gary's in a particularly notable area today because Gary's contacted us from Birmingham, Alabama, and Alabama is, of course, in all our news bulletins today for various reasons. So Gary asks, is the evacuation time the time to leave the atrium or the whole building?
Okay, that's a very good question. The evacuation time is for the atrium when you're talking smoke control for the atrium. And we really didn't get into evacuation time much. You need to not just look at the if you will, the fluid flow analogy of people moving out of the atrium. That time, you also have to look at pre-movement times, the time it takes for people to realize something's happened, then to make a decision, and then finally to move. And we realize that people will be standing there in the atria looking at the fire while it's burning, while they feel safe. And so, next question.
Okay, thanks for that. And next one, we're going south here. This is from Gerardo in Mexico. And Gerardo asks, does CFD or CFAST take into account the use of smoke vents?
You can, when you're doing a CFD analysis, you can take into account smoke venting, where you would, once the fire is detected, vents in the ceiling of the atrium would open up and the smoke would go out that way. And if you do that, your system becomes much more susceptible to wind than it would be if you were controlling it better and you had a roof up there and you were using exhaust fans. And because of that, I would encourage that kind of CFD analysis be done with that kind of smoke control analysis be done with a CFD analysis, and that you simulate an area outside of the atria looking at wind conditions to make sure that you're not going to have a situation where wind forces will push the smoke back down, which can happen.
Okay, thank you, John, for that. And that really goes directly into the next question. This is from Anne. We're going north here. This is in Canada. And Anne asks, could this analysis be done in FDS, which of course is Fire Dynamics Simulator, a CFD code?
Oh yes, FDS is the computer program that I've always used for atria smoke control analysis, and it is also validated and verified by the Nuclear Regulatory Commission. And it was developed specifically for fire, and it's free. So the free part is the one I love the most. Next question.
As long as it's free and it works, I guess that's the key.
Well, yeah, it also has to be good.
Very good. Okay, well, we're going across across a few miles now, so we're in Thailand, and this is Tale, and Tale asks, can the CFAST model be used to consider the thermal profile?
Oh, I think he means the thermal profile inside the atria when the sun strikes say, the roof of an atria, assuming it has a roof. It might be part of a building and this floor is up above. But when the sun can hit that, it can get hot and you can develop a warm upper layer. And that warm upper layer can be quite a few degrees above what's there. This is a tricky thing. I have talked to people who have told me they have done it and they can do it. I have always tried to rely on logic to get around it because I know that it's a tricky bit of business to tell the model that it has this hot layer up at the top and then get it to have that at the start of the fire. You have to fool around a lot. But yes, I've been told that you can do it.
Okay, thank you. Just reflecting back on the previous question, Tej, who's contacting us from Australia, so an early bird.
Yeah.
Tej asks, what CFD software might we use for tenability analysis other than FDS?
No, I don't know about another one you use besides FDS. FDS has a lot of features built into it that make it very good for tenability. You know, I know that others exist. When I started doing this, we used the model that was developed at Harwell Laboratories in the UK, at NIST, and we had to write Fortran code to do some of these things that we had to do to simulate the fire and a number of things. And if you have that capability with a CFD model, you can use almost any CFD model you want, but I can tell you, it's a lot of work. Next.
Okay, thank you. Is Tajay back in Thailand here? Tajay asks, Tale, sorry, asks, is there any difference in modelling the atrium to modelling a warehouse?
Okay, that's a good point. And everything that I've said here about atria applies to large volume spaces. And with the possible exception of warehouses. Now I know fire warehouses are large volume spaces, and the physics is the same with a fire in either one. But the difference is that with warehouses, we've stacked them with fuel pretty much up to the ceiling, or at least very high. And we don't do that with atria. We're normally looking at fires that are at the base of the atrium, not being terribly high fires, you know, as far as the fuel was concerned. And so we have a difference there. But yes, you can use this. You could use it for a warehouse. You could use it, not a warehouse. I wouldn't go that route. But for an airplane hangar, you could use it for sports arena. A huge number of large spaces can be, yeah. So next.
Okay. Very similar question. I think you've answered from Mohammed about warehouses. So we'll move on to a next question. Okay, this is from Diane, and Diane is contacting us from United States, Charlotte, and Diane asks, regarding the idea of adding exit signs to improve egress route visibility. She goes on to say, or he goes on to say, often the exit signs are not precise in the directional value, i.e. the wrong chevrons are uncovered, or none are. Is this part of the design specifics when it's given such heavy credit?
Yes, this is, you would have to work, you know, the whole arrangement with the exit signs in very carefully and get approval for what you're doing that way. And I think that's part of the reason that people prefer, or a lot of people prefer using reflecting signs, the visibility calculated for reflecting signs, rather than the one for illuminated signs.
Okay.
Next.
Okay, I've got a question here. This one was emailed in before we started actually today. This one was from the US. How can zone fire models be used to help develop design fires?
Oh, okay, yes. Using CFAST to do this, or another zone fire model, can save you a lot of time compared to, say, using a CFD model to develop the design fire. And you wind up with good, usable results that have engineering validity to them. Let me give an example. I'll describe a room with one sprinkler. And you can extend this logic to a room with many sprinklers. But in the room, you have a specific location for your sprinkler, and then you would locate your fire at a worst place location, and you choose that yourself, or nearly worst case, relative to the sprinkler. You would then input the room dimensions, the materials that the walls, floors, and ceiling are made of. You would put in the openings from the room. So now, see, we're really describing the room pretty well. You put in the location of the sprinkler and the fire, and then you would define the fire. And you define it the way that I defined the one in the example we talked about. And what you're really interested in is the initial part of the heat release rate, where we have the fire growth. You know, the fire curve is divided up. It's made of a number of different stages. We have ignition, growth, flashover, fully developed fire, and decay. And we would also put in the soot generation and maybe some other data as well. And then we would run CFAST, and it would come back with the actuation time of the sprinkler. Now, what we would do then is we would put in the curve that we used for the growth stage of the fire, and in the United States we would put that in going up to sprinkler activation. And then at sprinkler activation we would put in a curve, which is this is a empirical equation, and that's in the handbook for the decay curve. And so that's how we would do it in the United States. It's my understanding that in the UK, you would go with your growth curve up to sprinkler activation, and then you would have it run constant for some period of time, and then you would follow that with a decay curve then. And so you would deal with it that way.
Okay, well, John, John, that's pretty comprehensive. Just a reminder to everybody, this is being recorded. I remember to push the record button, and so you will be able to review this. And so that's quite a lengthy answer that John gave there, and you'll be able to review that at your leisure. John, can I move on to the next question?
Certainly.
This is from Joseph in New York, USA, New York. And Joseph asks, for your sofa example, did you use CFAST or CFD to calculate the visibility for the different atria?
Oh, I used CFAST for that, and my reason for that was to show that CFAST could be used to give an indication of whether there was a reasonable possibility that we might want to go through an entire design analysis for a smoke filling system. Because if you get terrible visibility when you use CFAST this way, then the odds are that if you spent all the money to do a CFD analysis, you'd wind up with terrible visibility as well. But the CFAST is not good enough to do the final design analysis. And so that's why I used CFAST for that, was just to give us an idea of whether it made sense to continue into the big, full-fledged and very time-consuming and expensive CFD analysis. Next question.
Okay, it probably answers one of the questions that was mailed in then. Why not just use CFD tools? Why bother with CFAST? Is it a matter of cost, John?
Yeah, it's a matter of cost. A CFD model for one of these things takes many hours or maybe even days to run. And CFAST runs in the time it takes to pick up your pencil. And so there's an enormous advantage in using CFAST. You can get things done, you can answer a whole lot of questions in a very few minutes, and it's especially nice like the developing the design fires. You can knock off your design fires in almost no time at all compared to what it would take with CFD analysis. Also, you have to understand there's a repeatability issue with fire. The real fires in the world are not terribly repeatable, and you're sort of getting like a general average answer when you're using CFAST, because it's based on these empirical equations, and that's really there's a nice comfort about that. When you use a FDS, you could make minor changes and get very big changes in your final answer. And so if you wanted to take into account the unrepeatability of an analysis, I think the CFAST does have an advantage in that, even though it certainly doesn't go into all the level of detail of analysis. Next question.
Okay, and just picking up one of your later question, which you can't see at the moment, but so you would use to get that detail, then you would use CFD to do the final detail.
Oh, absolutely. You want the detail, because you have to realize that the zone fire model doesn't simulate the ceiling jet up under the ceiling, and when they calculate sprinkler activation time, they use empirical equations for the ceiling jet to calculate sprinkler activation time, but the zone itself doesn't include that. And then down at the bottom of the smoke layer, the smoke is somewhat mixed in with room air, and the visibility would be better. And so you have a whole complexity of what's going on that's simulated, and it's much more like the physical world. And you could have a pocket of high density smoke that would be much worse than the other smoke, and you're very likely to pick that type of thing up in a CFD analysis where CFAST could never do it. So for the real analysis itself, I would certainly recommend going with CFD, or if you have a very simple, straightforward atria, you could just use the algebraic equations.
Okay, thank you. Well, that covers a question from Enquan in Ashburn. So let's move on to the next question from Matt. Matt's in the UK, in the southwest of the UK, and Matt asks, when using CFD, is it best to keep the model to a basic form, for example, where several areas are to be analysed at the same time?
Well, yes, it's the best thing that you can do is to, now when you mean separate areas, we have to sort of define what we're talking about. If we're talking about the main atrium space, and then you're thinking of separate areas as being rooms that are open to the atria, they have a doorway that's open, or a large walkway that's open, you really want to be simulating those with CFD right along with everything else. If you're talking about somewhere else in the building and it's separated by doors that are normally closed, you wouldn't really worry about those when you're doing your analysis of the atrium. Now, when you're doing the analysis for wind purposes, and sometimes we need to do that, we go, we simulate the atria and the outside, but in FDS we can change the grid space, and so we would have a nice big grid space for the outside of the building for wind analysis, and then we would have a much smaller grid space that would be appropriate for the needs of the smoke movement inside the atria. We would have that, and so okay, well, you can do those. Now you can run those separately, those analyses, but I think it's much better to run those analyses with the wind at the same time you're actually running analyses inside the atria to see what's happening there, because that gives you the wind that's actually going on. In other words, you're letting FDS make the connection between the outside, which is dominated by wind, and the inside of your atria, rather than trying to do it yourself separately.
Okay, thank you for that. A question from Dan in Belgium. Dan asks, can you take into account stratification in CFAST?
I think that we answered this in a way earlier. Stratification usually is a stratified layer of hot air at the top of the atrium, and we can do that. That requires some fiddling around to pull it off. There's also stratification in another sense, and that's that because you would have a hot stratified layer there, if you were relying on smoke detectors that were located up at the ceiling to activate your system, and you had that hot smoke layer, you could get a stratified smoke layer underneath it where the smoke didn't get through and get into the ceiling-mounted detectors, and so you had a very significant delay time in activating your system. And that, knowing how CFAST works, it's probably possible to simulate that, but I wouldn't do it. I would go with beam smoke detectors, so that we would pick up a stratified smoke layer with a beam smoke detector. And in fact, that's in NFPA 92B in the United States. We tell people that that's the way they should do it. If there is a chance of stratification, they should go that way so that the system gets activated. Once you activate this system, the fact that you had a hot layer of air up there is kind of irrelevant, because you exhaust that hot layer, the smoke moves up, and you start exhausting it right away. And so that would really be a detection issue. Next question.
Okay, let's try and get two more quick questions in, John, if we can, before we run out of time. This could probably take the rest of the afternoon, so please feel free to dodge it if you feel it's inappropriate. This question is from Alex in Cambridge in the UK. It makes a bit of a statement first, and then asks you a query. He says in the US, big fans are used to clear stairwells in flats, whilst in the UK, standards only have enough fan power to clear stairwells if fires only break out on one floor. This has been this is an issue of great debate in the UK at the moment. He asks, what's your opinion of the UK standards on smoke ventilation in stairwells?
Okay, I don't know exactly what the terminology is here. I can say what we do in the United States with no trouble. We pressurize the stairs. They're intended not to have smoke leak into them. You may have tiny amounts of smoke leaking in, as people would say, open a door to walk in and they say that they're on the fire floor. That smoke is insignificant. If they were capable of walking to the door, opening it up and going in, the smoke couldn't have been that toxic that went with them, and now it's diluted inside the whole stairs. So that's not a smoke problem, that little bit. And then we pressurize it to keep it out. Now, a smoke ventilation system, I have talked about the possibility here in the United States of doing these, but people would have to be using a combination of, at least as far as I see the thing, a combination of CFD modeling and network modeling like Contam, in order to evaluate one of these systems to verify that they would work as intended. I get the feeling the idea is that we don't try and maintain a pressure difference on these things, or we allow smoke to leak in. There could be maybe a door that's open on the fire floor or something like that, letting smoke in, and now we're trying to get the smoke out. And but I really don't know what the systems are, so I really can't respond to that other than just to sort of talk around the edges. Do we have another time for another question?
Yeah, I think this is quite an interesting question, actually. We got lots more questions, but this is one I picked out. This comes from Mohammed in Malaysia. And he asks, is this modelling method supported by fire insurance companies?
Oh, I have no. I'm not a businessman. I'm an engineer. I don't worry about insurance. My wife buys the insurance for us here, and so on. I don't know what they would accept or not
Oh,
accept.
okay, well, that's fine. I, we have to draw our webinar to a close. We've hit 2 o'clock here in the UK, and 9 o'clock in Eastern United States. So John, it just falls me to thank you so much for this webinar today. Just to let everybody know, this has been the most popular webinar that the CIBSE ASHRAE Group have ever held in the many years. So thank you, John, for providing a great opportunity for people, as you've heard, right around the world to listen in and benefit from your many years of experience.